But first, I will introduce you.
Yeah.
Hello, everyone. I think we're live now. Thank you for joining in, all of you.
Uh, One
Yeah,
more question.
yeah, we are already live. Yeah. So I think we have Shaif here with us, Muskan with us. These are the faculty members. Of course, Shaif in particular helped the kids a lot. And I think Souradip and Vethathiriyan are here, who are the main presenters of this particular research project. We are about to hear the one of the first research project coming out of the summer research program at Chinta. This particular project is titled Efficacy of Elliptic Curve Cryptography, a comparative analysis with RSA, and the two co-authors are Souradip Das and Vethathiriyan Krishnamurthy. Souradip is a 12th grade student from Kolkata. I think when he started, he was 11th grade, about 5 to 6 months ago, uh, with the research program. And Vethathiriyan is a 10th grader from Singapore. So, uh, Souradip, just I'll go to the first slide, and maybe you can start explaining a bit more about the project. And once you do that and tell me to go to the next slide, I'll go to the next slide. Okay. So, Shuradi, please start.
So the the topic of this project is elliptic curve cryptography and comparative analysis with RSA cryptography. The purpose is to show that how you can use elliptic curves as a method to uh, encrypt and decrypt messages from a sender to a receiver without any interference from any attackers, or in other words, a safe and secure transmission of a particular message from a sender to receiver. To start off with, in the first slide, we have the definition of an elliptic curve, which states that it is a curve that follows a specific equation of the form y square equal to x cube plus ax plus b, where a and b can be any constants. Uh, Along with that, there is also an requirement we have to follow, that is that the discriminant of this curve, which is 4a cubed plus 27b squared, the discriminant should be non-zero. This would ensure that the curve is non-singular, or it will not have any repeating roots. So all the
Okay.
roots will be distinct with each other. It could have one root or three roots, but the roots has to be distinct. With that, so we define a extra point O at infinity, which would be the a point that we define it as the identity element, where you perform several group operations, and it will not change the format with any other point on the elliptic curve. In general, the all the points as shown here, the set of points on the elliptic curve E are defined as all x comma y, such that y square equal to x plus b, along with the identity element that we just defined as O. So when with the point O, we define a group structure on this elliptic curve, and on the next slide we show how for any two points P and Q on the particular elliptic curve, we perform the group law, or the addition of 2 points. So this is as follows. First, we draw for first we choose any 2 points P and Q on the curve. They need not be distinct, they could be equal as well. Then we draw a line joining those 2 points. And if the points are chosen to be equal, then the line will just be a tangent to the curve at P. Next, we mark the third point of intersection, which we define as P times Q. We will mark that point as R on the elliptic curve. Next, we reflect point R along the x-axis, and we define that point, which could be R dash, to be the sum of the 2 points P and Q. So this is how we define a sum of 2 points on an elliptic curve. This picture shows how we have actually defined the sum for two general points P and Q on a particular elliptic curve. Next, we talk about a particular crypto system or a public key algorithm. So it is called the RSA algorithm, that was first developed by three mathematicians, Ron Rivest, Adi Shamir, and Leonard Edelman in 1977. The simple idea which was used to make this crypto system was just the computational difficulty of factorizing a particular large number into two large prime numbers. So it did, it uses a asymmetric key system, or in other words, a public key and a private key system. Here we show how to generate the public and private keys. First, we define a security parameter 1 to the power n, or in other words, the size of the set that we would be working on, which would be n bits. We define that as a security parameter. Then we generate two very large prime numbers P and Q, both approximately n bits long. Then we take the product of with as capital N equal to P times U. Note that taking the product is not a difficult task, but dividing n into the two large prime numbers P and Q is a difficult task. Uh, this is the main idea in this RSA key cryptography. Next, we take the phi of capital N, where phi denotes the Euler's torsion function, and this should just be p minus 1 times q minus 1. Next, we choose an integer, any integer between 1 and phi and n, such that the GCD with phi and n is 1. We choose this because we next define the private key D as the modular inverse of E modular phi of n. Uh, the GCD of E of phi of n equal to 1 part is crucial, because otherwise there won't be any modular inverse modulo phi of n. Then, so the private key here would be defined as uh, n comma d, and the public key, which will be accessible for to all, would be defined as n comma e. So yeah, so we have defined pk as n comma e, or the public key, and the private key as sk equal to n comma d. Now, with the keys properly defined, suppose a sender wants to send a message m to a particular receiver. So what the sender does, he takes the public key n comma e and the message m. We are taking n to be any natural number, and of course n has to be very smaller than n, because we have already chosen the security parameter to be n and the primes to be n bits long. Next, we compute the ciphertext C. We define it as C, to be equivalent to n to the power e modulo n. So this is the ciphertext, and we take the output. With the encrypted ciphertext, so the receiver will take the ciphertext and the private key that he has personally, which is not available in public. What he will do is, have to show this. He will take the private key, and he will decode the a message k, which is equivalent to c to the power d modulo n, and d is the uh, so inverse of e modulo phi of n. Now my claim is that this message k will be the exact message n that the receiver wanted to take as output from the sender. Now how does it work? Well, because what he was doing is that he is basically taking the message in and applying a power e to the e into d, which is basically, if you take modulo n, it will be just be n to the power k plus some l into phi of n, and so there is a printing mistake. It should be m to the power 1 plus k into phi of n.
जी.
How do we get this? Because d into e is basically uh, uh, any multiple of phi of n minus 1. So the remainder would be 1, and if we apply division algorithm, we will get a form k into phi of n plus 1. If we take the 1 out, we can write it as m into m to the power k into phi of n. And if we apply Euler's theorem on n to the power k into phi of n, modulo n, that would be 1, because we have chosen m to be a very small number, because n is a very large number and n is a product of two large prime numbers. So anything smaller than that has to be co-prime with n, or we can directly say that m and capital N are co-prime, and so we can apply Euler's theorem, and we will finally get the message in back again to the receiver. Now how? So in the last slide, while so if we consider eavesdroppers or outsiders, while they will have access to the public key, they won't. It will be difficult for them to figure out the private key, because to figure out d, which is the inverse of e modulo phi of n, we have to perform extended Euclidean algorithm on large prime numbers p and q. But to figure out p and q, they have to factorize n, which is extremely difficult, computationally extremely difficult. So this is why it can be considered safe and secure. Next, we come to ECC cryptography. This is also a public key cryptography like RSA, but it uses elliptic curves and ideas similar to that. So firstly, we normally define a elliptic curve E in A comma B as y square equal to x cube plus x plus b over a finite field. We define this finite field to be a where it is defined on two binary operations, addition and multiplication, over the rationals, and the final field is size of the final field is taken as f cube, where q is a very large prime number. Uh, Next, we choose a we choose a base point. Base point p could be any alpha comma beta, on the elliptic curve whose whose prime order is very large, and we call that n. Next, uh, we select a private key. So we directly select a private key first. In RSA, we have selected a public key first, then a private key from that public key. But here we are selecting the private key first, which could be any random NB, but it has to be less than it. And then from that private key, we compute the public key as PB equal to NB times P, where P is the base point directly chosen on the elliptic curve. Next, uh, suppose we take a plain text PM. In the next slide, we, we take a plain text. So any message, we define it as PM, which is on the elliptic curve of that finite field, and a random positive integer k. Then we construct the ciphertext Cn as uh, so k times p, where we apply the multiplication, and pm plus k times pb. So this we define as the ciphertext Cn. Then how can we compute the message? Well, it is very simple, because for the receiver he just has to take the ciphertext, like the addition operation of the ciphertext, which was pm plus k times pb, and just subtract it with the multiplication operation, but by uh, multiplying it again with kb. And because we had chosen pb to be equal to p times nb, the kpb and nbkp will cancel each other, and we will be left with pn. So the receiver will get the message pn, and then we output the decrypted plain text to the receiver. And how does it help to create a safe and secure transformation of message? Well, because since we chose a very large prime number k, while the public key was p, if you could should go to the other slides,
Which one do you want me to go to?
in slide 11.
Slide 11.
Yes.
Okay. Yeah. Oh, I see. Slide 11. Okay. I see. Yeah. Here we go.
Yes. Since we chose a large prime q, the private key was NB, but the public key was uh, PB equal to NBP. This was the public key, and the outsiders know of this information, but they do not know the private key. And if they have to compute it, they have to uh, first do PB by P, and this is a very hard task, because the base point has a large prime order n, and we have taken all this in a finite field where the size is a large prime cube. So again, it is a very computationally difficult task, and the outsiders will have a hard time figuring out the private. Next, we do a comparative analysis with RSA and ECC. So first we talk about encryption efficiency. RSA maintains a low encryption time, so it is very fast in encrypting its messages because it uses very elementary number theory concepts like modular exponentiation with a small exponent involved in RSA encryption, but it has a significantly high decryption inefficiency depends on the size of n as well, where n is the number of bits. But with higher key size, the decryption time increases significantly, and this makes RSA less ideal for scenarios where decryption speed is crucial. Next, we go to ECC or elliptic curve cryptography performance. ECC also shows a very high encryption efficiency, but slightly lower than RSA encryption time due to more complex calculations involving elliptic curve point multiplication. But ECC's decryption efficiency is ECC has a very high decryption efficiency, unlike RSA. It, it maintains low decryption times comparable to its encryption times because of the symmetric nature of point multiplications or due to the symmetric nature of the elliptic curve themselves. In conclusion, while ECC is recommended for systems where decryption efficiency is paramount, RSA should not be overlooked when encryption speed is crucial. The decision to implement either cryptographic standard should be informed by a nuanced understanding of the system's security requirements, ensuring optimal performance and robust protection. In other words, it depending on the system, we can use RSA and ECC to our benefits. So, thank you for your attendance. I will be stopping here, and my other com-
Yeah, thank
teammate.
you very much, Shorodip, and for the outstanding talk. I'll have a clap for you, of course. Very nice, very nice. I mean,
Thank you.
it's amazing that a 12th grade student and a 10th grade student, your co-author, is also here, can understand and work on such beautiful mathematics, and Shaif, of course, for guiding the entire thing. We should have Shaif's name here somewhere as a advisor, and Muskan as an additional advisor. We will make sure that happens next time. One thing I always say to the kids, and this is in general true, that if you are doing a high school level research project, you are really trying to do two things. The first thing is that you want to learn some deep mathematical science. So you want to actually learn something. You don't have to be street smart. You don't have to, prove a point to anyone. You just have to learn something beautiful. As this entire paper presentation progressed, I noticed that he used elliptic curves, of course, but apart from that, he also used elementary group theory, which is really awesome. He used number theory, which is part of course, the Olympiad program and so on. And a deep understanding of what's going on. And this is amazing. This actually does the first thing really well, that it demonstrates that they have worked really hard to understand the basics, which is fabulous. The other part is being creative. So work really hard to learn something substantial and then be creative with it, which is also fantastic. I think the way this I mean, all the summer research projects, I think 30 plus people are working, Shaif, together. Is that correct? Yeah. Okay. I think I cannot hear you properly, but yes.
30
Yeah.
plus students are working on this.
30 plus people are working together this summer on different projects. And I'm just waiting for to hear what other people are doing. I'm sure they are as amazing as this one. So thank you again. By the way, Shorodip, we have already recommended you for the. Are you in grade 12 right now? Is it currently in grade 12? Is that correct?
Yes,
Okay,
yes.
okay.
I'm good.
So you should be applying to American universities every year. We actually recommend some students for the full scholarship in our counseling programs with our partners like College Labs, for example. This year we are recommending you. Fantastic job, I think. You have been consistently doing really well. Shaif was also telling me how amazing
Thank you.
you were, and of course Vithan as well. Vithan is also really nice, but he's just starting out. He's in grade 10 right now. He's a young chap, and I'm sure more nice things will be coming from him as well in the future. uh, if you have any questions for the viewers, I'm saying if you have any questions or any comments, please feel free to share it with us. You can always email us or reach us through our website chinta.com, and and we will be very happy to communicate with you. For today, we are stopping out here. Again, I will thank the authors and the advisors, Shaif, Muskan, and authors Shorodev Vithan. And I'll see you guys in the next time. Bye. Take care.